Hey guys, I hope you're all doing good. In this video, we are going to be simulating a flow over a NACA airfoil. To get started, create a new project and let's create a new part file. And then we're immediately going to go to Insert, Curves, and we are going to select Curve through XYZ points. So this way, what we're going to do is we have this data file that contains the XYZ profiles or XYZ coordinates of a NACA airfoil. And with those points, SolidWorks is just going to draw a curve. So I'm going to click on Browse, and here make sure that you select text files, and then you will see the NACA text data. Now this file will be shared with you, so you don't have to worry. You can actually use it so that we are both simulating the same airfoil. Let's click on Open. You can see here that the coordinates are being populated. Just click OK, and if I zoom out, the airfoil has been created. So let's just put the model in the front view. So currently you can see that the angle of attack is 0, right? So which means that the airfoil is not tilted. The first thing that I'm going to do is select the front plane, and then I'm going to create a sketch. And then what I'm going to do is I'm going to select this curve, and using the convert entities, I'm just going to convert that into a sketch. Once I do that, if I zoom in here, you can see that the loop is not closed. So we're going to use the line tool to close this off. Okay, so now we have a closed contour. And finally, what I can do is specify an angle of attack at this point. So let's just click on this guy. And then what you can actually do is you can select Move Entities and click on that drop-down box and use a Rotate Entities option. So here what we're going to do is we are going to be selecting the entities first. So we need to select both our line and the spline, and for rotation point we are going to select the origin. Okay, so now if I change my angle, you can see that the angle of attack is changing. So typically it needs to be like this, right? So this is what you would call as an angle of attack of 10. All right, so I'm just going to go with this guy and click Apply, exit sketch, and once you have it, you can go to Features and you just extrude the geometry to something like this. All right, so that's how you create your base airfoil. At this point, it's a good idea to save the project. I'm just going to create a new folder called NACA test, and then inside that, I'm just going to save this part file. Okay, now that we have saved it, we can actually go to Flow Simulation, and then we can get started right away. The first thing that I would do is click on the wizard tool. And then here you can just give it a name. The project name can be Angle of Attack Analysis. Click on Next. So here we are basically going to go with default units and nothing to change here. So this is going to be an external flow, and we are going to be running a time dependent simulation. Okay. In total, we are going to be running the simulation for say 5 seconds, and we are interested in getting output every 1 second. Okay, gravity, you can turn it on if you want to. In this case, I'm not going to do that. Click on Next. The working fluid is going to be air. And if you're trying to simulate really high Mach number flows, you can just check this out. In this case, I'm not going to do that. So let's click Next. And then click Next again. Here, we want the X velocity to be 600 meters per second. Okay, so that's the speed of the flow over the airfoil. And then let's just click Finish. Okay, so that's our base setup. I'm just going to put the geometry in this view so that we can see everything. Now, if you select the computational domain, you can see that you will be able to adjust it. Before you do anything, right click and click on Edit Definition. We are going to be doing a 2D simulation. Okay, so what we're going to say is we're going to be simulating only the X and Y directions. Any gradients along Z directions is going to be neglected. So we select XY plane. Okay, when you select XY plane, the direction along which the case becomes 2D is the Z direction. I hope that makes sense. So let's click Apply here. And now what you can do is click on Edit Definition, and you can actually drag the domain size. Now, ideally what you need to do is the region after the airfoil, that is called as the wake region. So you need to make sure that your outflow boundary or your exit boundary is sufficiently placed. So something like this should be good enough. Ideally, people would do something like 5 times the chord length at the inflow and maybe 10 to 15 times the chord length at the outflow. So the distance between the end point of your airfoil and the right hand side boundary should at least be 10 times or 15 times the chord length. Now, depending upon your airfoil and flow conditions, this might change. So that is the typical range that people use. So in our case, let me just extend this a little bit more. Okay. And then that's going to be my computational domain. Now, what is the goal of my simulation? Well, there are a couple of things. So first, what I'm going to do is we're going to be looking at global goals. And for global goals, what we want to do is we want to look at the force, the total force along the y-axis and the z-axis, and maybe also the friction force along the x-axis and y-axis. Sorry, not the z-axis, the x and y-axis. Okay, so let's just click on that. And for global goal, right click, and then we're going to add a surface goal. So the surface that we are going to be selecting is going to be this guy, right? And in this surface, what I want is I want to integrate the entire force. So I'm going to be integrating force along x-axis, force along y-axis, and then let's just click OK. So that's my goal. And what else do I need? Well, I need to define my mesh now. So let's first look at the mesh. So I'm going to click on show basic mesh and put the geometry in, say, the front view so that we can see how the mesh looks like. So this is not a bad mesh. So what I'm going to do is right click, and then I'm going to insert a local mesh. So what does that mean? What I can do is I can actually select this surface on the top, and what I'm going to do is I'm just going to refine the cells over there. So that way what's going to happen is we are going to have cells that are really smaller near the wall, which is very important when you're doing airflow, when you're doing external aerodynamics. Now, there are additional considerations that you need to take into account. For example, by looking at the computational mesh, you can see that this mesh is not a body fitted mesh. This is what you call as a cut cell Cartesian mesh. Typically, it's not very well suited for external airflow, but it gets the job done. In addition to this refinement, we can do much more, but I think this puts at a very good position to run a basic simulation. Okay, so now that I've done this, I can run the simulation. So I'm going to click on run, and we're going to do a new calculation. And in my case, I have 8 processors. I'm just going to use all of it, and then we're going to run the simulation. So this time, as I run the simulation, I'm just going to be looking at some data. So let's just close these 2 windows. And what I'm going to do is I'm going to click on insert preview. And then what I want to do is I want to look at contours, say, of pressure. So what's going to happen is as the solution progresses, you can see how the pressure field evolves. Similarly, let's do goal plot. And this time we are going to be looking at the surface force. This is the surface integrated force, say, along the y-axis, and click OK. So that's going to be another plot. And what I'm going to do is I'm just going to tile all the windows, and you can just watch this to make sure that your solution is converging. Now, one general thing that I want to point out is when people typically run simulations like this, they look at something called as residuals. So residuals basically says how fine your transport equations or your governing equations have been solved. Now, the problem with just looking at residuals is sometimes it's not enough. So the better thing to do is to look at something like the drag force or the lift force and see if it's actually converging to a particular value. So you can see that my lift force is still changing, which means I should not stop the simulation yet. I should keep on letting it proceed. Okay, so we'll check back on the simulation a bit later, and we'll discuss the results. All right, so the simulation has been running for a while, and a couple of things that I'm noticing is that the average value for my lift is converging to a value, which is a good sign. Ideally, I would like to run this for a longer time. So currently you can see that, we have run about 1870 iterations, and it's pretty much flat, which means with subsequent iteration, things are not changing. And this is what you need to do to determine if the solution has converged or not. Now the other thing that I'm seeing here is there are some reflections here. So for example, the top and bottom boundary, well, we did not define any boundaries, but looks like there are some waves that are reflected from there. This suggests that, this particular length needs to be much more higher. That is, the height of our entrance and our height of the exit needs to be increased. But here the whole idea is we are just demonstrating how to set up an airfoil simulation. This is not a validation study, so we don't have to worry about it. Okay, so at this point, I'm just going to stop the simulation. Okay, so now I can just close this and then head back to SolidWorks. So here we first want to create a cut plot, insert, and then we always like to create XY plane plots. And then we are going to be showing the mesh and also contours. And let's maybe take a look at, say, velocity to start with. All right, so you can see that your velocity contours are there. A couple of features that you should notice is that you can see that near the surface, the mesh is being refined. So that's the refinement feature that we had enabled. And there we go. So that's velocity magnitude. Again, it looks a bit very choppy because the color is not a uniform color. So what I can do is I can just click here, edit. And then what I can do is maybe just increase the number of color segments. And that's going to give you a smoother looking plot. At this point, maybe just click on edit definitions. And then maybe just hide the mesh. And there you go. So that's going to be a much more smoother looking plot, which you can take images and then include in your reports. All right. So more importantly, we need to focus on our goals. So what I can do is I can just click on insert and let's just look at some of our goals. So for example, we wanted to look at the integrated force. So the integrated force along the x-axis, that's going to be a drag force, and the integrated force along the y-axis is going to be a lift force. So we can just click on show. Then you get the total value. So this is the data that you need, and what you can do is for different angle of attacks, you can calculate the lift force, the drag force, create a plot, and then calculate the lift and drag coefficient. So as part of your assignment, what I'm going to do is I'm going to ask you to change the angle of attack till stalling conditions reach, and then you're going to be making a plot of the drag force and the lift force, and you're going to be writing a project report on that. Okay, so I hope this video provided you enough information on how to set up an airfoil problem using SolidWorks flow simulation. If you have any questions, get in touch with us. All right, I'll see you guys in the next video. Bye.